This is section 10.7, Exponential Growth and Decay. How do we use exponential and logarithmic functions to solve growth and decay problems? These are very practical word problems that you're going to be doing tomorrow in class or the next day in class, and it's going to be imperative that you know how to use these formulas. There will be 3 formulas you'll be learning. Each of them have several variables. You'll have to know what they represent. The problems are not that hard to solve. You just need to try to keep everything straight. So these are very practical problems. If you're doing science, you're doing business, you're doing math, you will need to know how to solve these problems. Exponential growth. Let's suppose an investment earns 8% compounded annually. The value in the investment will be multiplied by a factor of 1.08 each year. So when you start, you have $100. After the first year, you're going to add 8% to that because that's what your 8% interest or 8% return on investment gets you. So after the first year, you're going to have $108. The second year, you're going to take another 108% of that, and you're going to end the second year with $116.64. By the third year, you're going to end up with $126. You notice that every year you're multiplying it by 1.08. So we can say that after year n, whatever number n represents, your total is going to be 100, the 100 you started with, times 1.08 to the nth power, n representing the number of years. You will notice that with year 3 is 100 times 1.08 cubed. This is what we call exponential growth. It's going to increase by the same factor every year or every period, whatever that might be. This is the compound interest formula. If an amount P, which we'll call the principal, is invested at an annual interest rate R, compounded n times a year, then in T years the investment will grow to an amount A by this equation. A equals P times 1 plus R over n to the nt power, where R is expressed as a decimal. So what you will see is there are 5 potential variables in this equation. In all these problems you're going to solve, you're going to have all of the variables except for one, and you have to solve for the missing one. So A represents the amount after however much time in T years. P is principal. Principal is another term for how much you started with in this case. R is the interest rate. You will often be given a percentage in a problem. You will have to convert that to a decimal. N represents the number of times it's compounded every year. So if it's quarterly, it's 4 times. If it's monthly, it's 12 times. N times T, T is going to be in the number of years. All right. So this formula looks like a mouthful, but it's really not that bad. And yes, you are going to have to memorize it. Example 1. How many dollars must be invested at 16% compounded quarterly to yield $10,000 at the end of 5 years? Alright, so the way I solve these problems is to list all 5 variables and see what they are. And here they are. A, P, R, N, and T. In this case, A is the amount that the investment grows to. In this case, $10,000. So that's a known quantity. P is the amount we started with. We don't know that. We're going to have to solve for P. R is the rate of interest. In this case, 16%, you convert to 0.16. N is the number of times compounded per year. Because it's quarterly, you're going to compound it 4 times. Finally, T is the number of years. In this case, 5 years. So you have 4 of the 5 values. You just have to solve for the 5th one. And now you just plug them into the equation. Here's your equation. And you plug in the values. 10,000 equals P times 1 plus 0.16 over 4, all to the 4 times 5th power. So let's simplify this a little bit. I took the log of both sides. I first changed this into 1.04. 0.16 divided by 4 is 0.04. So 1.04 to the 20th power. I took the log of both sides. Now, what you have here is a log of a product of 2 numbers, P and 1.04 to the 20th power. So you can apply first log 1 to make it log P plus log 1.04 to the 20th, and then you can move the 20 from the exponent to the coefficient of the log. So 4 equals log P plus 20 log 1.04. Log of 10,000 is 4 because 10 to the 4th power is 10,000. Alright, now let's keep going. We need to rearrange the equation, so we have log P on one side. So I subtracted 20 log 1.04 from both sides and switched the sides of the equation. So the log P is on the left. And you simplify. Log 1.04, you put in your calculator, you get 0.017. And so you end up with the log of p is 3.659. Now you have to use the 10 to the x function to find out what p is. So 10 to the log p is just p. So p is 10 to the 3.659 power, or 4570. So the original investment was $4,570. So in this question, you have to figure out what the original amount you started with is, and you have to use a combination of algebra and the various rules of logarithms that we covered early in the chapter. And you need to know how to convert logs to just the p, and you need to remember you have to take the log of both sides. Alright, our second formula is the doubling time growth formula. And this is going to deal with population growth, or bacteria growth. If a population of size n0 doubles every d years, or hours, or days, or whatever unit of time you want to use, then the number n in the population at time t is given by this equation. N equals n0 times 2 to the t divided by d power. And again, this is basically a situation where you have 4 variables, you will be given 3 of them, and you have to solve for the 4th one. And sometimes you might have to solve for one and then plug it back in to solve the problem. Let's see how this works. The population of a city was 3.5 million on April 1st, 1980, and 5 million on April 1st, 1990. Assuming exponential growth, find the month and year that the population will be 6,500,000. Alright, so we have a lot of things going on here. The first thing you're going to want to do is identify what the variables are. So, let's start with the 3.5 million and 5 million. We're going to use those two to solve for the missing variable. We need to determine the rate of doubling. That's the question that we want to know. The rate of doubling is going to be some rate in terms of probably years in this case. How long does it take for the population to double? So here are 4 variables for the doubling time formula: n, n0, t, and d. N represents the population at time t. So after time t is passed, our population in this case is 5 million. I'm going to use just units in terms of million. So population at time t is 5. N naught is the population at the beginning. Well, our population at the beginning was 3.5 million. So we're going to go with that. That's the population at time 0, which is why you see N naught. 0 is another word for naught. Alright? So we have 2 of the 4 variables. T, we know 10 years have passed since April 1st, 1980 to April 1st, 1990. We are going to solve for D. This is the rate constant, or the doubling constant. How long it takes for it to double. We're going to be solving for D. So let's plug these numbers into our formula and let's solve for D. Here's our formula. Let's plug the numbers in. 5.0 equals 3.5 times 2 to the 10 over D power. Now notice that 5.0 goes with the population after 10 years have passed. 3.5 million represents the original population. The reason it's a 2 here is because we're doubling. If we're tripling, it would be a 3. If we're quadrupling before, whatever. Alright, now let's solve for D. How do we do that? Let's simplify it. First, let's divide both sides by 3.5. So you get 2 to the 10 over D power is 1.429. Now, just like we saw in example 1, to get rid of a log, you need to take the power of the base to both sides. In example 1, it was 10. To get rid of an exponent, or to get an exponent by itself, you need to take the log of both sides. So let's take the log of both sides. So log of 2 to the 10 over D power equals the log of 1.429. Now you will use law 3 to move the exponent out to be a coefficient of log 2. So now you have 10 over D log 2 equals log 1.429. Now it's just a matter of getting D by itself on one side and doing the calculations on your calculator. So if you rearrange it, divide both sides by 10 and log 2, you get 1 over D equals log 1.429 divided by 10 log 2. And if you flip everything upside down, you get a D of 19.3358. This represents, I'll go back, this represents the doubling rate. It takes about 19 years for the population to double. Now what we want to know is how long it takes for it to reach 6.5 million. So we're going to have to come up with a new equation to do that. And we're going to use new values. Now our final population is 6.5 million. Our original population was still 3.5 million. But now we are going to solve for T. We know the time it takes to double. It's the amount we got after solving the equation first. 19.43 million. So now you have to solve for t. And this is very similar now to what we just did. And so you divide both sides by 3.5, and you get the log of both sides, and you use the third law to move the coefficient out in front of log 2. So at this point, you have t over 19.43358 times log 2 equals log 1.8571. Now we solve for t, multiply both sides by this number, divide both sides by log 2, and your t is 17.356 years. Now the question is, find the month and the year the population will be 6.5 million. So you can't just leave your answer like that. You know the 17 years is, but how many months is 0.356? Well, 0.356 years is the equal of 4.3 months. And if you want to know how to do that, just multiply that by 12. So you're going to be looking at approximately 17 years and 4 months. So the population will reach 6.5 million 17 years after the starting date. And 4 months. 17 years would make it 1997. 4 months from April would be August. So the population will be 6.5 million in August 1997. So this was a very long problem. The first thing you needed to do is solve for the doubling time. That allowed you to then plug the numbers back in with the new values and solve for the time it takes for the population to reach this figure. And if you're confused by this, I would encourage you to look over the problem again, go back, rewatch it, and see if you can follow along. Our third formula is the half-life decay formula. If an amount n naught has a half-life, h, then the amount remaining at time t is n equals n naught times 1/2 to the t over h power. This is a very similar formula to the doubling formula. The only difference is, instead of a 2 here, which represents the doubling, we have a 1/2, which represents the half-life. Alright, let's see how this works. Example 3. The half-life of radioactive radon gas is 3.8 days. How much of 100 milligrams of the gas will be left after 7 days? Alright, so again, you have a formula. You're going to list all 4 variables and solve for the one you don't know. So we have n, n naught, t, and h. N, we don't know how much remains, but that's what we're solving for. We know how much we started with. We started with 100 milligrams. Time, 7 days. The half-life, we're told it's 3.8 days. So again, you were given all but one of the variables. You solve for n. And this one's a little easier because n is the thing on the left. So let's plug those in. N equals 100 times 1/2 to the 7 divided by 3.8 power. 3.8 power. All we did was substitute. So all you have to do now is punch it in your calculator. 7 divided by 3.8 is this amount. 1/2 to that power is something you do in your calculator, multiplied by 100, and your n is 27.89, which means there will be 27.9 milligrams left after 7 days. Alright, so this was a relatively easy problem because all you had to do was plug numbers in and go straight through. You didn't have to take the log of both sides, you didn't have to take an exponent of both sides. This one is pretty simple. So again, solve for the variable you don't know, and if it helps you to list them all out, go ahead and do that. Example 4. One isotope of chromium has a half-life of 23 hours. How long does it take for 50 grams to decay to 40 grams? So again, I want you to list all 4 things and see if you can do this one yourself. You're going to have to either take the log or an exponent of both sides, so there's a little more math in this one than there was in the previous example. Alright, here are the 4 possible variables. N represents how much you end up with, in this case 40 grams. N naught represents how much you started with, in this case 50 grams. T is the time it takes. We don't know how long it takes. That's what we're solving for. H represents the length of the half-life, in this case 23 hours. So you're going to be solving for T. Let's plug them into the formula and see what we get. You get 40 equals 50 times 1/2 to the T divided by 23 power. Now, when you do these half-life problems, you should notice that the n is always going to be less than what you started with, because this is a matter of decay. When we did the doubling time problems, n should always be greater than what you started with because your population is increasing. And the same with the compound interest. You should always end up with more than you started with if you have a positive interest rate or percentage. Alright, let's now simplify. You're going to divide both sides by 50 because you want 1/2 t divided by 23 on one side, and so 40 divided by 50 is 0.8. Now, because you have an exponent, you need to take the log of both sides. So let's take the log of both sides. And I converted the 1/2 to a 0.5 because you can put in 0.5 in your calculator. So log of 0.5 to the t over 23 equals the log of 0.8. Now let's use the third law to bring this exponent to the coefficient of this log. T over 23 log 0.5 equals log 0.8. Now you simplify and solve for t. So you're going to multiply both sides by 23, divide both sides by log of 0.5. So 23 log 0.8 divided by log 0.5. Plug those into your calculator, and you see that t is 7.4. And don't forget, you need to write a solution on these problems because you need to give it some context. So it takes 7.4 hours for 50 grams of chromium to decay to 40 grams. Make sure you write a label of some sort at the end because this isn't just 7.4 by itself. Alright, so for this problem, again, plug in the numbers you know, solve for the ones you don't. Careful with the math. Make sure you know and feel comfortable how to take the log of both sides or take an exponent of both sides. Okay, 2 more examples to practice on. The population of Waterville increased 12% during 4 years. How many years are required for the population to double its initial value? Alright, now you've also got to figure out which equation you're going to use. Here you're talking about population growth, so you're going to use the doubling time formula. So, see if you can solve this one on your own and check your answer after you pause the video. Alright, here are 4 possibilities. N represents how much the population ends with. We want to double the value. So, the population at time t is 112 because it increased 12%. So at the beginning, we'll start with 100. Now, you can make this 1.12 and this 1. Either way, I got rid of the decimals just because it's easier. So, here, even though they don't tell you the original population, you know the amount of the increase. So the population times 0, you can call 1 or 100. Time t, it's going to be 112 or 1.12, depending on what ratio you use. In either case, this should be 12% more than this. N should be 12% more than N naught. We know the time is 4 years, so we are solving for the rate of doubling. How long does it take for the population to double? That's what we're solving for. Now you plug those values in, and you get 112 equals 100 times 2 to the 4 over d power. Divide both sides by 100, and you get 2 to the 4 over d equals 1.12. Now, because you have your variable in the exponent, you need to take the log of both sides. So let's do that. Log of 2 to the 4 over d equals log of 1.12. Now remember, the next step is to move the coefficient in front of the log. So 4 over d log 2 equals log of 1.12. Now what you're going to do is solve for d just like you did algebra. Remember, log 2, log 1.12 are just like numbers like you did before. So you get d equals 4 log 2 divided by log of 1.12. You punch those numbers in on your calculator, and your d value is 24.465 and change. So remember, d represents the time it takes to double, which means it will take almost 24.5 years for the population of Waterville to double. And this is based on the current rate of increase, 12% over 4 years. All right. Let's try number 6. How much will a $4,000 investment be worth after 5 years if it's invested at 8% interest compounded quarterly? All right, so we're back to the original formula that we learned first. Go ahead and try to solve this one. List the variables out. Find the one you don't know. All right, here are variables. A is the amount we're going to end up with, and we don't know that. That's what we're going to figure out. P is the amount you started with, the principal. That's $4,000. R is the rate of interest. In this case, it's 8%, so we rewrite it as a decimal, 0.08. N is the number of times interest is compounded per year. Since it's compounded quarterly, it's compounded 4 times. N is 4. T represents how many years? In this case, 5 years, so you put in 5 for T. Now again, this is very simple, similar to one of the examples where you just have to crank stuff out because you don't have to do any complex algebra to solve for A. So if you plug stuff in, you get A equals 4,000 times 1 plus 0.08 over 4, all of that to the what's going to be 20th power. So this is 1.02 to the 20th, and just multiply them together. This is pretty simple. you get A is 5943.79. So, after 5 years, a $4,000 investment will be worth $5,943.79. Alright, let's review the three formulas we learned today. We have the compound interest formula. A equals P times 1 plus R over N to the NT power. A is the amount you're going to end up with, P is the amount you start with, R is the rate of interest as a decimal, N is the number of times interest is compounded per year, T is the number of years. T stands for time, N stands for number, R stands for rate. For doubling time growth, N is equal to N naught times 2 to the T over D power. N is how much you end up with. N naught is how much you started with. The 2 represents the doubling. T is the time it takes to go between N naught and N, and D is the rate of doubling. In the doubling time problem or growth problem, N is always going to be bigger than N naught. Finally, the half-life decay. N equals N naught times 1/2 to the T over H. Very similar to the doubling time formula. The differences are, instead of a 2, you have a 1/2 because you're cutting in half instead of doubling. T remains the same. H represents the time it takes for the population to shrink by 1/2. In this case, N will always be smaller than N naught because you're going to have less after than you had at the beginning. This ends 10-7. This was a long section with a lot of problems. You're going to be able to work through the problems in class tomorrow. If I have you first period, you won't see me, but you'll have the answers somewhere posted, hopefully. If you're in period 6, I'll be there for 2 hours with you. You can't wait, I know. There might be something else for you to work on too, some review problem, so that you won't be totally bored for the 120 minutes that you'll be in class. Alright? If you have any questions in the meantime, please contact me or ask me in class before or after school.